So this is kind of like an intro to infer.net, and in our context it's with March Madness, and that's just kind of an example. It started out with Kyle Deterding and I, who might be showing up later. He's at something. He works downstairs for Hudl, and we decided to use the Halo-style matchmaking to make a algorithm that would predict the NCAA tournament. And it uses infer.net, so we'll kind of show you a little bit about infer.net, and then what we did, and then how we did, and then maybe some extensions to that. And so just to give you like really, we stole a lot of these slides, or at least adapted them, I guess would be the cover your ass term, from John Wynn and John Weaver or something like that. All these really smart Microsoft research guys in the UK. And so this is what infer.net is. It's a framework for running Bayesian inference and graphical models. And so what are graphical models? Who cares? It's a bunch of words. But it's basically, if you can model it, it can like apply machine learning, and it can make like predictions for you, and it can infer things, which when you infer something, it's like you thought you knew something about it, and you got some new evidence, and now you know something else about it. So it's like, if I were to infer, if you were telling me that you flipped a coin 6 times and it was heads, 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 tails, heads, heads, I can tell you what the probability of the first coin that you flipped being heads was from that, or something like that. You know, it's just drawing conclusions on data that you may or may not have. And so that's where the first like infer.net, like the hello world for infer.net, is the coin toss. And so the first thing you'll notice is it's kind of funky. It's a variable bool, and that's not a variable in the normal sense. It actually means that somewhere that there is a variable that's of type bool that's first coin, but we don't necessarily know what it is right now. And so it, in this case, it's actually a range. It's a Bernoulli, which means that variable 50% of the time it's true and 50% of the time it's false. It could also be like a Gaussian curve, which I think we've got on another one. And so you just say, I know that the variable falls in here, and here's the distribution that it is associated with it. And so you can do things like, set the variable, assign it a distribution, and then you can assign another variable that's some operation on those two. So if you say, okay, my first coin is going to be heads 50% of the time, second coin is going to be heads 50% of the time, what's the probability that they're both heads? And that is just simply, first coin's true and second coin's true. And so it uses an inference engine, which that's literally all you have to do. You don't really have to worry about how that works, because that's the nitty gritty. And then it'll just tell you, the probability that both coins are heads is 25%. And then don't worry about the rest of that. So you can also, like I said, have like Gaussians. And so this would be a Gaussian variable, which is centered on X, has variance 1 or whatnot. And so it's going to fall off. And so the nice thing, like that's cool, I can do statistics too, but the nice thing is you can do things like put constraints on your data. And so in this case, we're going to give it this variable Gaussian, but we're going to constrain that it's always greater than 5, or 0.5, because we just know something. Something about our data said this value is always greater than 0.5. And so from that, you can do things like pull distributions from that. And so you can say, I know it's greater than 0.5, now what's my new distribution, and it'll give you stuff like that. And the nice thing about infer.net is you don't have to really, you do have to think about the model, but you don't have to think so much about the math. These are all stolen from Kyle, all these slides. But one way you can do it, like let's say we wanted a threshold, and so that 0.5, if we want to move it up, we want to say like, what's it look like at 0.1, 0.2, 0.3, 0.4, 0.5. You can just do it in a for loop. And that's cool, I guess, if you're into being slow. You'll get these results, who cares? It's just numbers. But the nice thing is you can instead tell it that it's a, so you can instead like give it an observed value. And so you make threshold a variable, as opposed to here where we made threshold, just a double. Instead, we can make threshold a variable. And we always say that X is greater than threshold, but we actually go through and change the observed value of threshold. And so where you'll get a lot of boost here is that it won't have to recompute the model every time. One thing Infer.net does is it actually will like compile your model into a DLL. And so you'll lose a lot of time if you're constantly compiling these models. But if you can kind of like parameterize your data out to where it's just like takes in something for your variable, then you can do stuff like this, and it'll just run through the model really fast. And so this will be about 10 times faster. But it's just really weird because you have to think of them, you know, as variables, even though they can or cannot have, they may or may not have like real values. It's just weird. So by now, I think this is everybody, except you don't have donuts, you have sandwiches. And you don't have guns and grenades, you have cell phones.
I have guns and grenades.
Except Chad.
You just can't see them.
And we've kind of spoiler alerted already, but what can it be used for? Well, this is what they use for Halo TrueSkill. Halo 3, I should be more specific. Halo's gone through a few evolutions of different ranking algorithms, and they all have people that like them and don't like them. But this is what Halo 3 is, and they think it works pretty well. And so basically, one of their problems was, I mean, there's 12 million players on live, there's 2 million matches a day, and each of those matches has, you know, up to like 8 or 16 players, and there's 2 billion hours of gameplay. And so they wanted to know, how do we see really how good are you at Halo? I think for Chad it'd probably be negative, but they don't factor in. And so what they want to do is they call it TrueSkill because they're trying to find your TrueSkill, but one of the things is it's like a hidden variable. You don't actually know what my skill is. It might be like 23.3, but this system will never actually probably find that, but it'll get really close. And so we estimate our old skill. So if we all got in a sweet, super awesome LAN match here, and we all had previous skills, we'd look at how people did, and then we'd give a new estimate of that skill after that. And every skill has a skill level, so like a mean. They say stuff like skill level because it's the Xbox people and they're not maybe the math people. But you'd have like a skill level and then a mean. That would be a mean, and then a variance, which is your confidence in the skill level. So somebody like Sully here hasn't played very many games, and these are from 2 different games as well. There's 2 different curves. So Sully would be average of 25. We're just going to say that's average, but we really don't know. He could be anywhere on this curve. Slow Play's played a few more, so we're pretty sure he's about a 19 or 20. And Sniper AI has played a ton. And so we're really, really certain that he's about a level 30. And so as you play more and more, these curves get a little bit tighter and tighter until you're pretty sure what that is. And with TrueSkill, they actually got it to where I think it's less than 20 games, and they're like 95 to 99%. They're confident that this is what your real skill is. And they want to know that because they want to match you up against people that are in that same skill. And so after a game, and this is where the math gets kind of tricky, so either ignore it or call my bluff or whatever. Just disclaimer, I don't understand all the math probably as well as I should. But so Sully used to be here, but he got first place. And so what they do is they look at kind of like where, what's the probability, so Sully's TrueSkill lies in here somewhere, and Sniper Eye's TrueSkill lies in here somewhere. What's the probability that Sully's is actually higher than Sniper Eye? And we're pretty sure Sniper Eyes is in here, and so it's not very probable that Sully beats Sniper Eye. And so since he's got a low variance right now, we're going to move him up quite a bit because he must be a lot better than that. Sniper Eye, you know, there is a chance that he gets beat by Sully, and so it kind of takes a look at where you're at and where all your opponents are at. And so if you play somebody that's if like you play Sniper Eye, they're pretty sure it knows where that is. So if you're way over here and you beat Sniper Eye, there's a very low chance that you should have actually beat Sniper Eye because you've been playing for a while and your skill's pretty low. And so you'll probably shift a lot more. Whereas if you hadn't been playing for very much and it wasn't sure, you'll shift, but Sniper Eye might not move down very much because, you know, Sniper Eye lost to you, but we really didn't know how good you were yet. And so it starts getting, it starts to kind of even out where you're at, and it always is trying to make that curve slimmer. Does that make sense? Okay. And half of what I said there was probably wrong, but you guys all believed it.
What happens if you improve and get worse over time?
If you improve, well, it'll adjust. It's just once you get kind of locked, it won't adjust as much. because you'll be playing people that are pretty close to your skill. And so that's where a lot of the people in the forums complain about this stuff is, oh, it's not real and it's it's screwing me out of my whatever you get for being good at Halo. So yeah. And so if you look back here, it's kind of funny because they say months of work and hundreds of lines of code. And to us, that doesn't seem like much, but they do a hell of a lot in these hundreds of lines of code. And just another disclaimer, these are all like functional programming guys, a lot of them. And so it'll look like they have an F# DLL for it, and it'll look a lot like, I don't know, probably like Haskell or something like that. But it's all in .NET. This is all C#. And so they're saying, okay, we've got these 3 players, and these are their old skills, and so we're going to construct that, basically that graph. And then we want to see their performances, and those will actually be centered around their skills. And so we want to say, like, this is the amount that they could play outside of their skill, and we would allow it. And that part's very cloudy for me. But I just accept it, because the next thing you do makes sense, and that's you have the outcome. And so this just says, all I know about this data now, my new observation, is that player 1 is better than player 2. That's all I know. And so this doesn't take into account how many points they got. It doesn't take account teams is complicated, but this is just one-on-one battle. All we know is player 1's better than player 2, and we'll let the statistics decide the rest. And we know that player 2 is better than player 3. And so what you can do once you've kind of observed those outcomes, you can tell the inference engine to go back and say, okay, now that I know that player 1's skill is actually better than player 2, what do you think player 1's real skill is now, given all that data that you have? So does that kind of make sense where they're pulling that? Okay, but it's literally all black magic, and this is pretty much all that you have to do, and you'll get it going. So what we did over a few beers at Brewski's, I think, we decided to look at the NBA season. This was just the easiest to get data on. And so we just got this list of games in order, and we really simplified it down here because we only have one-on-one. We don't have to worry about 3 people, and we have to worry about a bunch of teams, but it's only one game only has a winner and a loser. So we get the winners' mean and variance, we get the losers' mean and variance as their previous skills. We create a variable of their performance, which we don't actually know, but all we know is that team 1 was better than team 2, etc., etc. We get the new mean and variance and just set those to the winners and losers. So we ran this on the NBA data. Kyle's more knowledgeable about this, but the championships were actually that year, the Los Angeles Lakers in the West just whooped the 76ers in the East. And you can see their records are about even. Their skill is quite a bit down, but that doesn't necessarily mean anything, because if you look at the Bulls, they're probably not better than the 76ers. So we realized here that we had a few problems, and we started to tweak some things like our beta, like how far people could play outside their range. And then we also realized that maybe maybe we started them off the wrong way, or like the seeding, or there wasn't enough data or something like that. But it was fun and just got our feet wet into it, and it was interesting.
I think one of the takeaways here is that when you're training a learning algorithm, the data that you're using to train it is very important.
Yeah.
Getting the right amount of data, the right type of data.
Mm-hmm. And so what we did is we kind of looked at like what the Bulls did, like at the beginning of the season and stuff. And so one thing, if I remember right, the Bulls either really started strong or ended strong. And you can see, like, if you start strong, you're going to have a lot of shift because you got a really low confidence in your skill. So if you start the season really well, it's going to help you out really a lot. And that's something that we didn't really know how to account for. And it's something we saw later on too. But it is March, and so we had to... the NCAA isn't great at giving out stats, but there are ways. It took me about 8 hours to scrape all this, because every team has a page that links to other teams sometimes have other games on there. It was pretty ugly. But we got about 11,000, a little over 11,000 games and over 1,000 teams for this year. And so you'll notice like some of these teams don't actually have their full season on there just because the NCAA doesn't even track their schedule. But they played somebody, like Nebraska loves to play really easy non-conference schools. I'm guessing a lot of Nebraska schools on here were not even in the NCAA system. They're probably not even real schools. No. Colorado School for the Blind.
Creighton.
Bam.
So we just straight up ran it. We gave every team an equal playing field. We realized that 30 games isn't probably enough, especially because they aren't playing each other a lot. Like 30 games, 1,000 teams. You can do the math. It's pretty sparse. But we did get some interesting things. Middlebury, which I don't think actually made the tournament. We're up there. Williams, but Connecticut, Kansas, Ohio State, you start seeing these, what most people would consider decent teams until last week. But one thing we definitely realized is that it was a fair thing, and we probably should have biased it. You'll notice Nebraska is about where they should be. The reason I have Milliken highlighted is that's usually the shirt I wear when I play basketball over lunch, so that makes sense because it's about how well I shoot for layups. And these are just the bottom. It's not formatted very well, but we have a mean and variance for these. So a couple things we did is we went through and found all the BCS schools, which was not very automated, but we gave them like a plus 2.5 advantage. We didn't see that much change. It was very surprising. It would flip a few, but honestly, Old Dominion was always in our top 15, and it was just weird. But they started the season really well, and they ended the season really well, so that kind of explains it. We also did it with just Division I teams. Again, it affected the order, but it didn't affect our bracket almost at all. But it was fun. It took a long time to run. I think we could have optimized it a lot. It took about half hour, or 20, 25 minutes to run on our machines, but it's not multi-threaded. We tried multi-threading it and it got pissed. I don't think the framework is designed for that. It ran through the first 2 to 3,000 games and then it would barf. So this was our numbers, and then we just plugged them into our tournament bracket. So our bracket now, our national championship pick was UConn. So we're still alive. It was our only correct pick in the Final Four. We had Old Dominion in the Final Four. And an interesting thing, or I guess that's coming up later. So an interesting thing about the Final Four is only 6% of ESPN brackets have their national champion in the Final Four. We consider that a win. And in fact, Kyle dug all these stats. It's 3 times more likely that your champion didn't even make the Sweet 16 than that it made the Final Four. So we were pretty confident about that. And a lot of that's luck, but right now our bracket's better than 71% of the brackets on ESPN. After the first 4 games, we were 1 for 4, and after the first day, we were in the 10th percentile. So we were a little nervous, but it turned out that we were all right in the end. And so what we didn't have, which a lot of people didn't have, Indiana State reaching the Elite Eight and Arizona losing in the first round. We did have an interesting thing, though, on this Butler-Old Dominion game. We had Old Dominion in the Final Four, and no matter how we weighted it, Old Dominion was always in the Final Four. They would beat, I think, Kansas in the Final Four. The next highest ranked team, or I think it went Old Dominion, then Kansas. The next highest ranked team right below that was Butler. And so if we would have flipped that, we would have had Butler going. I don't think we would have had them going to the Final Four. We would have had them to the Elite Eight. It would have helped us. But we didn't want to mess with the actual numbers. Or no, they would have made the Final Four. So we missed ODU, but at least the team that beat them, we had right behind them, and they did well. And we correctly predicted the 4 of the 5 top 4 seeds that failed to reach the Sweet 16, including Pittsburgh, which is kind of cool. So here's our actual bracket. And this is a little bit different from the one I have in the NG pool just because I typed them in wrong. This is a little bit better, which is why I'm showing you this one. So I guess it was a little unsettling to have Old Dominion in there. But other than that, it doesn't look too bad. I mean, we've got Kentucky and UNC. Those aren't too bad. We got Kansas and Notre Dame. We had Old Dominion, Florida, UConn, and we had Duke instead of Arizona. But as far as in these, it was kind of a crapshoot in the first round games, and it is for everybody. So we had Utah State over Kansas State, and we had Wofford over BYU. Our assumption was Wofford played a easier schedule, but we didn't take that into account. So if we were to do it all over again, I would probably weight the top 25 coming out of the gate or something like that, or maybe not. But the real interesting thing is how it did in the Nebraska Global Pool. Right now, it's tied for 9th. Emily, you were right. You got more potential than we do. And this is the one I put in, so it's screwed up. You'll see here it is beating Doug, which is very important. It's also beating me, which is very important.
Beating Doug is not all that hard.
Yeah, and if I would have put the correct picks in, we would be up here tied with Berta and Emily with 57 points. And we would have a higher potential too. But right now, if Connecticut... See, I don't know. I think, Emily's going to beat us regardless. So, but we could get second. We have the potential to get second depending on how Connecticut does.
So you make Emily.net?
Yeah. So we were really nervous coming out of the gate, but we were really happy once we got at least our champion in the Final Four, which I don't think many people have. Only two. Only two. So, and then I'm not saying this is magic. It's really lucky, but it's glad that at least we're glad that it was at least able to compete with everybody else. So why does this matter? Infer.net was used to make the Connect. That matters to me. It's really good at taking those statistical models and running inference on them. They developed a whole form of programming, backwards message passing and stuff, just to use on this. And the guys that did this did the magic in the Connect. You can watch videos that say that. I used to just say that assuming, but there's videos that have record of that. And so it's really good at working with large collections of data. It's really good at doing all these statistical things that you normally don't do. Normally a variable is a variable. But they can do a lot of things like linking things back. And so one way they do this, and this is really technical, you probably don't care at all, but they can do it with ranges. And so it's kind of like when we varied the threshold, except it's even faster. We can basically create an array of thresholds that we want to say, and then set that observed value to that array. And so this X or whatever, we could just say, I think we're missing some stuff, but for X we could just give it an array of doubles, and that would be a range that it could go over. And it's kind of like writing a for loop all in one line. You say for each value of X, assign it this data. And there's some more interesting and hopefully more things that make sense examples. I think that'll be in here. But yeah, so here's where a range would come into play. So our data is just a length of 100 or something like that. And this range is just 100 basically placeholders, I think, that you can assign to X. And then you'll notice here, the tricky part is you're indexing X not with a number, not with a numbered index, but with that range. So that's basically where you're saying assign every X over this range to this value. So we're going to assign to a Gaussian for each of those values. It's a weird way to think about things. You kind of have to. I don't think metaprogramming would be the term for it, but you kind of have to think beyond your simple variables, which is kind of tricky. But yeah, that's basically it. Infer.net, I'll take you to their website. It is not infer.net because that is some parked website. But it's created for Microsoft Research out of Cambridge. You can use it for, they use it for obviously coin flips. You can use it for, they use it a lot for clinical trials. So So if you want to know, how many people have the disease given that they've tested, all that statistic stuff, they can do pretty well. And they also have some cool things like the Monty Hall problem with the 3 doors and the goats and the car and whatnot. And then they also have things. Let's see. They have a few things like they used it to classify images. I can't find it. I'd have to find it, but they use it to classify images, and so basically you're taking like these weights on these features or something like that, and you can kind of like trace them back. And so given that it passed through here with this certainty and then through here with this certainty, if you find out like your training data that this is actually true or false, like you can infer back and adjust those weights. And so one of the first things I did, created a model of the Teammates project, where these weights are different like attributes. So the Teammates project's it's Match.com. It's trying to match mentors with mentees based on interests. And so I was saying like, okay, what's the weight that they like music the same, that they like the same classes or whatnot, and it would go through all the data, and I would tell it whether it was like a good match or how good of a match it was. And then based on that, it would kind of learn like, okay, this is a good match because this is high and this is low. And so you can actually get like a weight of how important each one is, and then also the covariance. So just because they match on music might not matter, but if they match on music and activities, that really matters. And so they can give you like, it's called a covariance, so it's how much like pairs of things adjust the outcome. And then you can use that to predict. So you can say, given these 2 potential mentors, what's the chance that they're going to be a good match? And one thing we learned there was what the heck is a good match. And so it really matters what you're actually measuring. And so with Teammates, we could say a good match is what do you think it is, but really it should probably be more data-based. So, how many years have you been together or something like that? And actually a way to do that, they have a way to take like bias out of paper submissions, which is pretty interesting if anybody cares at all. But it can, I'd have to find that. But it would like look at all your submissions, and if I'm a pretty nice guy, I think sometimes, and so when I would be submitting things, I would approve a lot more than Ben would because he's a jerk. And so we can go through and look at all the papers and see like what I rated them, what Ben rated them, and then find out like what. So if we're rating them 1 through 5 stars, it could look at all the data, not only the ones I rated, but the ones Ben and I rated, and say, okay, Nate's actual 5-star is actually like 3.5. Anything above a real 3.5, he'll give a 5, just because he's a nice guy or something like that. And it'll give you the actual ranges of those like reviewers, and then from there you can find the actual rating because you take the bias out and you can find the actual rating, which is pretty cool. That's a little more tricky than math, but so yeah, that's basically it. I don't know what questions do people got on it. Did that make any sense? I guess would be the questions. Yeah, Ben, wake up.
You mentioned giving different weights to college teams based on each season top 25 or something.
Yeah.
Doesn't that kind of defeat the purpose of the algorithm?
Yeah, it does. It does, but we thought it would give us better results. So, I mean, there's something to be said for like strength of schedule. And if you don't know that ahead of time, you treat every single game the same, which maybe you should, but I don't know. It's up for debate.
So how does it just determines the rank based on this team played this team and they won? It doesn't look like this was a better team and they won?
Well, yeah, it looks at how good the team was that you beat, but that team could be good because they beat up on a bunch of, not so good teams. And you don't really know. So if Nebraska beats VCU and VCU was good, but that's because VCU beat all these no-name schools, that game of Nebraska v VCU doesn't really know that. And those no-name school teams might not be bad yet because they might have some wins too. So it can't like look backwards and forwards. All it knows is like it's completely isolated to I know how good this team is, or I know how good I think this team is, and then I know how good this other team probably is, and that's all it looks at.
So does it run the algorithm like in order of the date the game was played?
Yep. Yeah, that was one thing we almost didn't put in. So yeah, it goes on the date, and so we tracked it every 200 games, and so you could see teams start to get sorted out, and a lot of teams fell out as they started getting beat. But if they were already at the top, 5 games into the season or like 5 dates into the season, and somebody beat them or they got beat by somebody, like that was already factored in, and then they would drop. So and doing it the way we did it is a little bit unusual because we're going back. In Halo, like you're always real time, and you're always looking, okay, for the next match, what am I going to be? Where we should have, I mean, maybe not, we shouldn't have from a data perspective, but we knew how good teams ended up being at the end of the season, or roughly, and we didn't factor any of that in. So.
Did you try running it backwards ever?
Backwards.
So
Start with the last game.
Oh
start
no.
with the last game, because it seems like you put a lot of weight on that. The first 10 games you would run through.
Mm-hmm.
Or run the games at random.
Or run the games at random, yeah. No.
It's like
That's a good idea.
That algorithm isn't really perfectly suited for this.
Yeah.
Looking
Right.
backwards is a lot better in real time. So
We basically put blinders on it now,
Yeah.
so it'd still be interesting to run it backwards though.
Yeah.
Maybe I'll do that today.
I like that because you're playing your conference games, which are going to be your toughest games.
Yeah.
So I think those should hold more weight.
Yeah.
And momentum. Going into the tournament.
Yeah, we didn't build momentum into it.
Did you have 1,100 teams?
Yeah.
I see that. There's only 350 teams
In Division One.
division.
We went all the way to Division Three, and then teams that weren't on the list of NCAA teams were on there.
I guess wouldn't that end up skewing your data quite a bit? I mean, if you're trying to predict a Division One tournament, having lower.
Well, that's what we did. We put those weights in. It didn't really matter. Any of the teams that had a full schedule, they were pretty accurate. So somebody who actually plays 30 games versus Division One or Division Three opponents. But it would pretty well weed out people that only played 3 games because they're UNK or whatever. So we did try and weight that, but it didn't affect it very much. It was kind of surprising.
Did you see how Williams College did in their postseason play, or
No.
whatever the top 2 teams were that
Oh no, we could. I don't know.
division they were in?
Middlebury and Williams.
Yeah.
We can look.
Instead of going down to those other divisions, wouldn't it have been easier to just say those teams are probably terrible? Hard to code,
Yeah,
so-
but we didn't want to bias it too much.
We'll not take that into account.
Yeah. Because if you're trying to
Because
bias
Division One
divisions.
rarely plays
Oh, great.
Division Two or Division Three, and if they do, those games don't count.
See, they only lost 2 games. I don't think they play. They're in the whatever that is. Oh wait, here we go. No, they won. Or they're in the NCAA semifinals. They won this. No, they lost the semifinals. Sorry. So they did pretty well. They lost to St. Thomas.
St. Thomas was another high one in the West, I think.
Was it? That'd be
I
cool.
don't think so.
So really, what we should have done is kind of segmented it out. Yeah, St. Thomas was up there.
Nice.
We should look at that tournament. Where do I find that tournament?
What division is this?
Varsity.
It saved you, might have saved you 4 hours of scraping data.
Yeah, but their data was so messed up. I had to go through it 3 times, so I just figured I'd get them all.
Anything to keep Nate out of real work.
Yep, exactly. Well, this is at night. Okay, Middlebury, St. Thomas, Worcester. Worcester was up there too.
And there's Williams.
Yep.
It said Williams up there.
So
It's
So,
like the final 4 was.
we had the
in
final
top
4
10.
for the division. We could have picked the Division 2 or whatever pretty well. So I don't know. Lesson learned, I guess.